The title of the talk is High Performance Computing in the Cloud. And I just want to do a bit of context setting up front. I'll start with on the right-hand side who this tutorial is not for. And I'm not going to be talking about optimizing an HPC cluster if you're really deep in this space and you've been doing it for a long time. You're thinking about optimizing like hardware in the operating system kernels, or you want to build an HPC infrastructure to compete with OpenAI or something. We're not really going to be talking about that kind of scale. We're going to be talking more about how do you make the concepts from HPC more accessible to data scientists. The company that I work for, we often talk about kind of reasonable scale machine learning or AI for companies that aren't necessarily Google, Microsoft, the FANG companies. Um, if you want to maybe make it more accessible to data scientists with good enough performance in a way that's easy for software engineers to maintain. Um, so that's really going to be the focus of the talk rather than kind of building from the ground up, like how do you do custom optimizations to CUDA kernels or something like this. So if you're looking for that stuff, very interesting topic, but not really what we're going to be going into today. So the agenda is to start off just by kind of introducing like what is the connection between HPC, AI, and now the cloud? Then we'll go into like what actually makes AI workflows go and how do you access these kinds of the kind of infrastructure that you need to make that happen in the cloud. And then finally in part three, we'll kind of bring it back to Python land since of course we're at PyData, and we'll see how can you do these kind of core primitives that you need to run AI workflows in a style that's much like HPC workflows. How can you actually do that from Python code in a way that's natural for scientists who are more used to interacting at the Jupyter Notebook and Python script level than say logging into some sophisticated HPC cluster and kind of understanding how to interact in that kind of system. Cool. So I'll breeze through the first section just to kind of motivate the topic, and then I'll pop back over to the chat and maybe answer any questions as we move through the different sections. So the first thing I want to kind of get on board is that like people are moving to the cloud. This isn't really a secret to people in software engineering. It's been happening for over a decade. And the pandemic really accelerated the desire for especially businesses to move workflows to the cloud where they can have more flexibility around how they just access the economics of doing especially computationally intensive jobs like we're talking about today. Um, Also, another big trend that's happening right now is that everyone knows AI is hot. ChatGPT, Stable Diffusion, all these models in the last couple of years have really like have brought AI into the forefront of people's minds, even outside of the engineering and software development communities. So companies are looking to invest, and developers are being tasked with building systems to maybe use these APIs, or for businesses that really want to kind of have their own positioning and their own defensible moat around AI to actually start to build some of this stuff themselves. So now just going right into like, okay, why does compute play a role here? Like, what's the connection between the desire to build our own AI systems and the desire to increase our capacity to do high performance computing? So this is coming from a sort of seminal paper from the 2020, I want to say, maybe 2021, that came out of OpenAI called Scaling Laws for Neural Language Models. Basically, what they point out in this paper is that they trained a whole bunch of different neural networks that are kind of shaped like these GPT models architecturally. And they demonstrate in these three simple loss curves that there's kind of three main contributing factors that are leading to the models performing better. The first one, and the one that they kind of argue is the most important in this paper, is the size of the model, just the number of parameters that you're storing in RAM as you train the model, and then at inference time, of course, as you make predictions. The other is the size of the training data set. So for language models, this is measured in tokens, which is like little chunks of words. Maybe it's like a little bit bigger than a word, maybe a little bit smaller, depending on how you tokenize the data. But anyways, the number of these tokens in the training data set that the model is exposed to is the second kind of scaling factor that they point out has a huge effect on the ability for the model to learn. And then finally, there's also a relation between these two and compute, the capacity to actually like run the operations that allow the model to learn, to update the weights, the parameters in the model as it sees new data and learns kind of how to keep predicting the next token in the case of pre-training these large models. So the relationship between the number of parameters and the size of the data is essentially what they're pointing out in this paper is that as you continue to increase the number of model parameters, there's a very direct correlation, and something that is like one of the things AI researchers are the most confident about right now is that if you keep raising the number of model parameters, the model is getting increasingly sample efficient, is the upshot of this paper and has been validated in research since, where if you keep increasing the model size, on average, like of course there's edge cases to this, but on average, people are finding that the models are able to learn and achieve the same performance on evaluations, seeing fewer samples in the data. Additionally, something that came out of this paper that I'll call back to in a few slides, and maybe it wasn't as in the forefront of people's minds at the time of this paper, is that the optimal model size is also growing with compute. So there's kind of a complex relationship happening here because I just said we get more sample efficient with more model parameters, but then also we're kind of having this relationship where maybe the optimal size of the model parameters just depends on what you can do, like what kind of computers and how many of them you can access. So the big claim from this paper, though, like putting that compute point aside, is that as you increase your compute, essentially what they're pointing out here is that you should focus more on making bigger models instead of growing a bigger data set. Was kind of part of what they're claiming here, that the improvements that they were seeing were growing faster with the size of the model than the size of the data set. Now, a couple years later, some researchers from DeepMind, the research lab that's been very much in the news this week, and is kind of the main competitor of OpenAI, they released this paper that's known as Chinchilla in some circles. The title of the paper is actually called Training Compute Optimal Large Language Models. And essentially what they point out is they say, hey, hold on, like it isn't just about increasing the model parameters. That's not like strictly more important. And they run a whole bunch of benchmarks of their own demonstrating that actually scaling the training data set size, the number of tokens in that data set, is as important as scaling the number of model parameters with compute. But if you look at this plot on the left side, the thing to notice is that there's a same through line. So even though the kind of like the punchline of this paper is countering what OpenAI said in their previous paper on scaling laws, there's the same through line of there's a clearly optimal model parameter size for each compute capacity. So these bowl-shaped curves here are essentially showing that as the color goes from this light green to the dark purple, we're increasing our compute, meaning we can keep getting better and better models. But there's this like bowl shape, meaning that there's an optimal value for how big of the model we can make, and it depends very much on how much compute capacity that we have. So we're kind of in this world now where we know that more sample efficient learning requires more compute, but then also if you can't keep increasing your compute, there's going to be worse performance eventually. And kind of the challenge here is that if we look at the plot that's on the right hand side now, it's showing that all of the models that are the most competitive are exponentially growing in model size. So kind of all of this together means that it's an extremely important capability for people to have the ability to kind of access serious compute power if they want to have their own AI systems that are reasonably competitive. So then the question becomes, how do you actually increase compute? How do you increase that parameter C in the three parameters that we were just looking at in that story? So there's a couple ways. Vertical scaling is the first one, and then horizontal is the second we'll talk about. So what I'm showing here is that on the top, there is basically you can kind of get a bigger GPU. Say you're using a V100 card from NVIDIA, you could upgrade that to an A100 card. The more recent generation, it's going to have more RAM, it's going to have more throughput, kind of all the things that you need to increase this compute capacity. On the bottom, it's arguable whether this is actually vertical scaling. Some might call it horizontal. But what we're basically saying here is like you could also go from a machine that has one V100 card to a machine that has 4 of them or some number of them. So this is like maybe if you're in AWS land, you could say I want to go from a P3 2x large instance to one with 16x large that has 8 GPUs on it or however many. So basically the point is scaling up on one machine to have more GPU cards. The other way, which is more of this HPC style scaling that we're kind of talking about today, and is the kind of the real way that you can extend C, just depend, like it becomes like a less of a how is this technically possible, and it becomes more of just how much can you invest in continuing to add more nodes into this cluster is what the economic problem becomes. Where essentially instead of trying to pack more GPUs onto the same machine, we start thinking about, okay, we know there's going to be 4 GPUs or 8 GPUs per machine. How do we now connect these machines in a chain, which is something we just can just kind of keep repeating that process. Um, Now I want to come back to the AI piece of this. But before I do that, I'm actually just going to exit the slides and just double check the chat if there's any questions. Oh, thanks, Tom. Yeah, exactly. Yeah, if you're interested in this stuff, definitely check out the paper that Tom linked. Okay, so I'll go back here. So now I want to connect this whole, like I talked about kind of the scaling way where you could add more GPUs or you could add many machines with more GPUs on each of them. Now I want to connect this to the neural networks actually, like these, what are these models and how do they relate to what the GPUs are? So there's 3 approaches I'm going to talk about: data parallelism, model parallelism, and pipeline parallelism. And the first one is this notion of data parallelism. So on the left-hand side, just kind of consider that as the scenario that we're in. We have this neural network, this model, where these gray lines connecting the nodes in the neural network are the weight matrices. These are the things that we actually need to store somewhere inside of a GPU's memory, and then we need to update them to, that's what learning is in deep learning. Then we have these little green squares. The green squares are representing data sets. So this is the training data that we push through the model, and then we use that to learn how to update these weights, the gray matrices in this picture. And then the third kind of graphic we have over here is there's got to be some way to then connect these purple squares, which are still representing the GPUs in our cluster that we have available to. So each one of these is kind of like its own computer, its own process. So this first case, we're talking about a technique called data parallelism to train the models. And this is something that people do when the data set is too big to fit in the RAM of a single GPU. So if we can't fit this green square on any of the purple GPU boxes here, we need to split up the data set, and then we can fit the entire model in this case on the GPU, on each GPU. So, but then we split the data set so each GPU is only ever seeing kind of a shard of the data. In this case, we have 4 shards. But again, the entire model is sitting on the GPU. What this looks like in PyTorch code is, I mean, this is obviously pseudocode, but essentially, like you can pass the entire model to the GPU device for that instance. We'll go a little bit more into this and see examples later in the tutorial. But the point here is that unlike a technique we're going to look at next, the entire model exists on the GPU, and then we're just passing parts of the data set. What's important to realize about that is that the forward pass through the model, so the model is making predictions while it's training, these are kind of independent of each other. Each model has its own copy of the data. Then after we push those predictions through, we get some like gradient computation, which is the way that the models learn. Not really going to be a tutorial on this. That's like a very, very in-depth research topic, is like how to actually do that gradient syncing. That's not really what we're talking about here, but this is a very important research path to consider. So anyways, after we do those independent forward passes, there's some way that these different worker nodes, these different worker GPUs now need to coordinate those gradients and kind of pass them over the network, however you connect these GPUs or CPUs together. And then we can also, like, once we get those gradients, we can independently do backpropagation on each machine. So this is one way that you can kind of think about how to do distributed training of machine learning, is this data parallel way. Now, another technique is called model parallelism. And before, with data parallelism, we were saying the data set was too big to fit in the VRAM of each of our processes. In this case, we're saying that the model itself is too big. So there's too many parameters in these models. Like you may have heard GPT-3 in their paper, they say they use 175 billion parameters. If you think of kind of how many, like what is the floating point representation of that? Say you use float 16, that's going to be like way too big to fit in the GPU RAM of the biggest processors that NVIDIA makes and are reasonably available. I mean, they make some nowadays that are crazy expensive and can do these kinds of things. But anyways, for all intents and purposes, there becomes a point where if you want to train a model that's that big, you need to actually break the model itself up into different parts and then send different parts to each GPU. So in this case, we see something like you kind of are splitting this first layer on the first GPU, and then you're putting the second part, the second layer on the second GPU. And what this looks like in the PyTorch code is, say you kind of have these two different, you kind of like break the model itself up into two chunks, two different objects, and then you can send each of those different chunks of the model to different devices using kind of the very high level APIs that PyTorch makes available to you. But all the modern deep learning frameworks will have some API like this to send different parts of the model to different GPUs. What's interesting about model parallelism relative to what we were looking at with data parallelism is that the forward pass for each data point, for each batch of data, actually becomes dependent on other GPU workers in a way that it wasn't in the pure data parallel case. Similarly, then the actual ability to do backpropagation becomes dependent because part of the model that you need to kind of get information from is on a different GPU in order to do these things. I won't spend too much more time here, but the other thing to realize is that you can combine data parallel with model parallel, and that's really the state of the art for doing these like very high scale, very high throughput AI training workflows. The final thing I'll point out here is that there's something called pipeline parallelism. My graphic looks like it got cut off here. But with pipeline parallelism, what we're talking about is basically making model parallel more efficient. Where that thing that I said, where if I want to push, say we have this neural network that has 1, 2, 3, 4 layers, like 4 of these kind of gray connective layers between the neurons, and we break each of those 4 layers up onto its own GPU. In order to do the computation for the second layer on the second GPU, the first layer needs to complete. And then similarly on the way back, in order to do backpropagation on the first layer, we need to have the result of the backpropagation on the second layer, so on and so forth. So people have very cleverly realized that, okay, if you just kind of wait for one batch of data to do this, you're going to have a bunch of time where these expensive GPU workers are idling and not doing any useful work. So we can break the batches up, data up into smaller chunks, and then we can kind of increase our utilization of these resources by kind of threading these different chunks cleverly. There's a whole bunch more techniques that you can kind of layer on top of this stuff. And this, again, is a really active area of research to look into, but these are some high level concepts for getting started. Cool. Now, coming more to like getting into like more of the practical part of this tutorial is the transition here is essentially like, how do you actually do this stuff in practice? And this is where the thread to coming back to HPC and more like traditional high performance computing workloads comes into play. Almost all of these deep learning frameworks are either actually based on MPI or conceptually based on MPI, which stands for Message Passing Interface, and is a protocol that's existed since the early 90s to essentially run exactly these kinds of jobs, where you want to log into one computer. That computer knows how to talk to a bunch of other computers in the cloud or in an on-premise data center. And you can just run one command from that main computer, and then all the other workers just kind of contribute their resources towards getting the job done. So connecting that idea then to like what does it look like to actually run code in these deep learning frameworks? Like we'll see in a little bit here, what like a live demo of what this actually looks like. The main thing I want to point out on this slide is that there's a whole bunch of different ways to run the same code in deep learning right now. So PyTorch is probably the most common way to write your Python code for deep learning. And if you want to run it in this way on doing distributed data parallel or model parallel, you can do it through any of these frameworks, and there's plenty more that aren't listed here. Torch Run is one that's supported by the PyTorch team. where you can see it's very simple in your command to just kind of say how many nodes you want to run on. MPI can also run the same program. And then there's this new thing from Microsoft called DeepSpeed that essentially builds on top of Torch Run and has a whole bunch of optimizations that Microsoft researchers are using to train their models. Now, two more points before we kind of get more into the cloud infrastructure part of this tutorial and talk that I want to point out are more just kind of like product considerations or kind of internal tooling considerations if your organization is seriously considering going down this route. One of the main things that, in my experience, and that I've heard customers from the current company that I work at and previous companies that I've worked at talk about is that AI research gets blocked when researchers need to do a lot of context switching between thinking about research code and kind of being in the mindset that you're in when you're iteratively developing in a Jupyter notebook. And they need to switch from that mindset into figuring out how does my compute cluster work, or why isn't my job getting submitted correctly to AWS batch or to Kubernetes cluster, or wherever you run the Torch Run DeepSpeed MPI commands on. And then the other main point to think about is that we are working in teams, and these workflows are running on very expensive hardware. And the infrastructure to actually make this possible, we don't want to be underutilizing it. We don't want one person to be monopolizing all of the use of that. And kind of at the same time, like the people who actually have to manage these compute layers, the platform engineers, the DevOps engineers, these type of people, it's very hard for them to consider like, oh, we should just separate it all so each scientist gets their own compute cluster. Or maybe we do one Kubernetes cluster over here and one Slurm cluster over here. This kind of adds operational expense to these people's workflows to kind of have to maintain and manage many different queues of work like that. But at the same time, scientists just kind of want to submit their job. And again, they want to separate their concern of, I want to do the research of making AI better and kind of iteratively improving our data sets and our models. I want to separate that from like, how does the model actually run and where does the data actually come from and connect to the compute layer. Cool. So those are just some considerations. Not going to propose any sweeping solutions to this, but I'm going to show you a bit of a demo of how you, in this section towards the end, how you can kind of get started going down that direction with a tool called Volcano that helps you basically do this kind of stuff on Kubernetes in a way that really is going about this problem. When researchers are working in teams, how do you kind of help people share the resources that are in the compute cluster? I'm gonna go ahead and pop back to the chat quickly, see if we have anything. Yes, I'm actually gonna share the slides right now as well. So if you go to this GitHub repository, the slides are in this PDF, and I see that people are sharing links in the chat. The links in that PDF are hyperlinks, so they're gonna go out to all the papers that people are linking in the chat as well. Awesome. Okay, so now what does this infrastructure to do these kinds of things actually look like in the cloud landscape? There's three boxes here. These are kind of noisy, like the way that they're positioned on this graph. But essentially, the way that I'm thinking about it in this visualization is that on one axis you have the operational expense to maintain these systems. This is kind of ignoring that there's a huge upfront cost as well that you should consider. But this is more like kind of the steady state consideration on the cost measure. And then on the vertical axis, we're thinking about the effort to get going. Like how much engineering skill do you need? How much are you going to need to kind of invest in R&D to get this up and running? In the bottom right, we kind of have what I would consider the one that's going to kind of increase your operational expense the most, but is going to be the easiest to get started. And it may even be the most cost effective if you're a team that doesn't have a bunch of very skilled Kubernetes engineers or cloud infrastructure engineers. These are the options that each of the cloud providers is going to kind of sell you as a prepackaged service. Things like SageMaker, Azure Machine Learning, Google's Vertex. These solutions are able to do things like distributed training, and they give you very high level APIs. They're not super flexible in terms of what you can actually do on the compute cluster itself, but that's part of the value that they're providing and charging you a premium for. Then in the middle, we have this layer that's more of the platform as a service model. Things like Google Batch, AWS Batch is the longest existing one. And we'll actually see a demo towards the end of this talk of how to use AWS Batch to do distributed training. And then on the top layer, we have this more like kind of DIY custom infrastructure, things where you can get really high levels of control, things that you can run in your own on-premise data center. So you could take, like theoretically, you could take the same exact code, run the Kubernetes code to do this distributed training on the cloud, then also run it in your data center. Same thing with Slurm. Um, and I think the idea here of this talk, really like the punchline of the third part of this talk, is that if you have a good AI development platform, whether it's some wrapper that you build around Google Vertex or SageMaker or AWS Batch, or it's kind of a homegrown Kubernetes cluster, things like this, a good AI development platform should ideally be moving you down and to the left on this graph. These charts now are kind of comparing some of these different solutions on a few of the different questions you might want to ask. It's definitely not complete, and it's kind of an eye chart. I don't want to like kind of just read it line by line. So again, I shared the PDF in the chat. Folks who want to kind of look at this and comment on it would be much appreciated. But yeah, you can read through these in your own time. I think the main thing to think about is just that there's a lot more questions than this, and these are kind of the basics of how do you form the cluster, how do you submit a job to it, like what kinds of supply chain do you actually need to have to get the compute nodes in this cluster up and running. And then of course, probably the most important one, I think, for the kind of platform engineer types to think about, especially if you're going to be doing this homegrown cluster on your own, is how are the different nodes going to communicate? And how are you going to install all of the network interfaces and things that make that fast? Because that's the biggest opportunity to kind of build an efficient system. And it's also the biggest potential risk to have a very inefficient system that makes things like GPUs become more of a cost sink than really driving value for you. So now I want to consider, like, there's a lot of people that are interested in Kubernetes right now, especially like the customers of Outer Bounds and the people that we tend to work with. So I wanted to just kind of have a brief aside on sort of this do-it-yourself, more custom infrastructure path and compare two leading options right now. So the two options are Slurm and Kubernetes. Slurm is much older and has been around for a while and has been focused on HPC since its beginnings. Essentially, it focuses on this notion of a batch job where you want to submit some workload to run on multiple different nodes. You want to make sure that all the nodes that you need to run the job are all available before you start running it anywhere for efficiency reasons. And this is referred to as gang scheduling. That idea that I have 4 different computers, 4 different workers, and I don't want to waste the resources of 3 of them by scheduling the job partially if I can't access all 4 of them at once, because I know that this job is going to need that much compute power to run efficiently. Slurm also has a lot of features around priority queues. So this problem that I was talking about around there's 10 researchers all trying to contribute, all trying to submit jobs to the same compute cluster. How do you fairly share the resources of that compute cluster so that one person doesn't just submit a bunch of jobs and then block all the other researchers from getting their work done? So Slurm has been around for a while, as I said, and it's very established for HPC and AI training. And then there's Kubernetes, which for the past decade has kind of been the new kid on the block and is more of a general system. And it has really, really strong momentum in the developer ecosystem. So Kubernetes is typically in the machine learning context more considered as a solution for serving models and doing things at inference time, because it focuses on things like auto scaling and kind of cloud native features of like packaging up a Docker container, a tight computer environment, and kind of being able to scale to many different nodes dynamically, things like this. But it's historically been less focused on these kind of big training workloads where the computers are each having 8 GPUs on them or something like this. But more recently, there's been a lot more pickup in the Kubernetes community of people trying to actually move these batch workloads into a system like Kubernetes. One of the knocks or one of the things that people might say about Kubernetes is that it's not really scalable in the same way that Slurm is, or that it's not built to do batch jobs. But I think there's been some recent evidence that kind of dispel that that, where essentially like OpenAI has written a blog saying that's what they're using to train GPT-3, Clip, and DALL-E, is that they've made a custom Kubernetes cluster that has 7,500 nodes, so maybe the biggest one in the world. And then even more recently, the X announcements, Elon Musk's AI around Grok, they also in their announcement post discussed that they are using Kubernetes in their training and inference stack. Another point here, another angle to consider this from is that the cloud itself is becoming competitive as a global supercomputer. So historically, it's been like these national labs and kind of government facilities that have the biggest supercomputers in the world, sometimes the academic clusters. And it's almost been sort of a joke in the HPC community to run the HPC jobs on the cloud, just because it's going to be very inefficient and very expensive, XYZ, and like the benefits of the cloud, like the dynamic kind of economics benefits of using the cloud don't really apply to HPC. That last part may still be true, but the fact that the clouds are now becoming serious supercomputers is kind of undeniable, as evidenced by this recent ranking of the top global supercomputers, where Microsoft's Azure cluster is now ranking up near kind of the most optimized clusters in the United States. And I think this list is actually even global as well. So very impressive by the Microsoft team there. Okay, so now I want to get into a demo, do something live. So what I wanted to do is make it as easy as possible to get started with one of these systems. It's called Volcano, for using PyTorch to write the code and then submit the code on a Kubernetes cluster. And then once you've submitted the code on a Kubernetes cluster, you can kind of start to like expand this out towards adding nodes into your Kubernetes cluster, just rewriting the PyTorch code a little bit as a distributed job, so on and so forth. So if you want to follow along, this link here, I'll paste it in the chat as well. Oops. Paste this link in the chat. It does require a bit of setup. You need to have Docker on your computer. We're going to be running Minikube as a Kubernetes cluster, which is a way to kind of run a Kubernetes cluster on your local computer. And the reason that we're doing that is just to make it really, really easy to, in a couple minutes, get started with doing this. Now, of course, in practice, you're going to want to do this on a full scale Kubernetes cluster that has serious cloud resources behind it, or is running in your data center with whatever kind of GPU workers you have on it. But this is a really quick way to kind of get your hands on, get the feel of what it's like to work with these systems. And then the same code will be runnable and kind of the same installation commands will be runnable on your cluster. So this is kind of a good way to practice is why I set it up this way here. Okay, so I'm gonna go to the repository and just kind of show you that link that I shared in the chat will take you to here, the TorchX local part of this repository. And I'll just talk through this README because that's basically all that I want to do in this section. And then, yeah, so I've kind of also like prepared things. So we'll see. It looks like we're doing pretty good on time actually. So maybe I will do it from scratch, but we'll see. So what we're going to do is install Minikube, and Minikube is this solution for essentially inside of Docker. So if you're on a Mac, you can install Docker Desktop, or if you're on a Linux box and you just kind of have Docker installed already, you can do this. If you're on Windows, it's going to be a little bit more challenging. You need to run the whole WSL system, but you can pretty easily find like Docker installation. So kind of depending on your system, you can go to this link and find out how to install Docker. Again, if you don't want to follow along here, no worries. You can follow along after and reach out to me on the Slack channel that I'll share in the slide deck. And I'd be happy to help you anytime. If you want to just kind of sit back and listen, that's totally cool. Okay, so once we've installed Docker, then we can install this thing called Minikube. So there's a separate link here in the repository to install Minikube. It should be very easy. It's kind of one command install. For example, if you're on Mac, I just did brew install Minikube. And then after that, we're on a Minikube start, which this will essentially form a tiny Kubernetes cluster on your computer. So this is pretty mind-blowing to me. Like I'm not really a Kubernetes expert, but I kind of know enough to like get by and kind of communicate with the platform engineers that set me up to do a lot of this stuff. And it's pretty amazing that you can sort of replicate the experience of the most powerful compute clusters in the world on your laptop and kind of have the same developer experience as somebody who's actually interacting with those seriously powerful clusters. Another thing about Minikube that's interesting to think about is if you have a bunch of on-premise GPUs, or maybe you have a DGX box, or you bought something from Lambda Labs and it's sitting under your desk, you can actually run Minikube on those boxes as well. So you don't have to do the full-on like cloud deployment to get the value out of Kubernetes. Like all of these same arguments will apply on local hardware as well. If you want to kind of string together several GPUs and have the skills to kind of connect them into the Minikube cluster, you can just run it like this as well, which is another really fast way to get started. So let's actually just verify. I've run this before, kind of did the cooking show, get things prepared a little bit so you could avoid seeing me muck around in the command line too much. But let's actually just verify that we're kind of seeing everything here. I'll make this a little bigger. So I'm in VS Code. This is on my local computer again. And what you see here is that I'm running the Minikube cluster. And when I type kubectl get nodes, this is kind of like the Kubernetes command line tool, the Minikube node shows up. And we can describe the node then. So you can use this command and then we'll use the name of the result here. So for everybody who's installed Minikube, you should just see this unless you're also already running other stuff on Kubernetes locally. Let me just go ahead and run that. So again, when I do get nodes, there's going to be the Minikube here. If you have a bunch of other nodes running on your Kubernetes cluster, which in practice, that is what it will look like, is say if you have 20 GPU nodes or something, you'll see a different node when you do the kubectl get nodes command in that case. But this will just print out a whole bunch of metrics about what's happening on this node right now. So you get a whole bunch of things like labels and annotations. This is all kind of like fancy Kubernetes engineer stuff. Like if you're more in the data scientist AI realm, like you don't need to be focusing on this. It's kind of part of the idea, but it can be extremely useful to have the basic experience of going through a tutorial like this, just to even know what questions to ask the Kubernetes admin that enables you at your company, things like this. Okay, let's keep going. Another thing, this part's optional, but I definitely recommend it because it's a pretty cool way to kind of get used to interacting with a Kubernetes cluster, is that Minikube comes packaged with a dashboard. So that's what I have up here. And what you can see is kind of this really nice user interface that shows you all the different stuff that you can do in Kubernetes. And then it's actually going to be like, it's going to be interactive and it's kind of plugged into the Minikube cluster that's running on my computer right now. So you can see all the different Kubernetes objects that you can create, things like a cron job. There's this concept of deployments. Today, we're going to be looking at pods, which is like the fundamental unit of Kubernetes. If you're not familiar with it, it's kind of like an abstraction that's like one level higher than a Docker container. Anyways, yeah, there's a bunch of good stuff in here. And this is where we're going to kind of verify. And so instead of just like seeing everything happen in the command line, we're going to want to verify in this interface what's happening in the Minikube cluster, just to kind of give a little bit more interactive feel. So once you have Minikube installed, then we're going to install this thing called Volcano. And remember, kind of the end goal here is, I should actually just start here. The reason that I want this Volcano thing to happen is because I want to use TorchX. And TorchX is this system to run your PyTorch code in a distributed way. So earlier we saw the command for like how to kind of do the MPI commands. It's very similar to this. It's just a way to submit a command to the compute cluster and then have that job get scheduled on the compute cluster. And the way that TorchX is working with Kubernetes, so is the way that TorchX can communicate with this Minikube cluster or the cluster that's going to be running on your cloud or your on-premise data center is through these Kubernetes objects that are enabled by the Volcano system. So that was kind of a lot of jargon. I'll pause just for 1 sec to see if there's any questions. Looks like we're good. Cool. And maybe I'll actually just take a 1 minute detour just to fully flesh out kind of what Volcano is and why we're using it here. But it's a project in the Cloud Native Computing Foundation, and there's a lot of interesting companies that are backing it. Mostly companies from China, actually. People like where's the yeah, here we go. The supporters from like Huawei, Tencent, Baidu. So like some of the serious players in the cloud engineering space in China for sure. Um, yeah, essentially what Volcano is allowing us to do is to schedule these batch jobs, these gang scheduled jobs, and to kind of put them behind some queuing system. So it's like I can say I need 4 GPU worker nodes, each having 8 GPUs to run this job, but then maybe our company only has 8 such compute nodes. So it's like there needs to be some way if we have several researchers that are all trying to compete to kind of get access to those resources at work. There needs to be some way to kind of have a queuing system so we are sharing those resources fairly. And then also making sure that, say, we have a production workload, we don't want that to be getting kind of intercepted or to be getting preempted by me just running some random experiments on any given Tuesday. Um, so, okay, that's a super high level of what Volcano is. What we need to do to actually make Volcano accessible inside of the Minikube cluster or any Kubernetes cluster is to apply this command. You can go ahead and see like what the Volcano CRD is, or like what this installer is, by going to the GitHub repository. But what this will do is it'll just create a bunch of different Kubernetes objects essentially that are custom to Volcano that enables all of this to work. So I've already run that in my cluster, so that I could just kind of keep going here without too much pause. But you will need to do that before any of the stuff below this is going to work. So like if you want to run these torch X commands, you can do this Docker one, but you won't be able to do the Kubernetes ones until you run the Volcano installation. And then finally, there's some pip dependency, and this is the Torch X package itself. So again, I've already run this. It's inside of my Conda environment for PyData, but you can install that on your computer like any package you want to install from PyPI. Okay. Okay, so let's actually run something. So what I want to do is first show you that TorchX works independent of Kubernetes, and then show you what it looks like with Kubernetes. So what we want to do is just run this very simple script. So you can imagine this is like a training routine for PyTorch code. So this could have your neural network training, this could have an evaluation step, whatever job you want to submit. Let's like think that this hello world.py file is any script like that that you want to submit to the Kubernetes cluster that has your PyTorch code in it. So in this case, what we're doing is we're going to pass one argument to the code. So maybe I'll just change it just to demonstrate that we're actually interacting with this code here. So we're calling the hello world.py script here, and then we're going to pass one argument. So we should see hello, comma, the result of that argument as the result. And the way that the TorchX part of this command is working is that we're telling it to run this job, and then we get to pick a scheduler. So this is kind of the core functionality of TorchX, is that what I'm telling it to do here is in a local Docker container, run this Python script on top of that container, and then in Docker language, like add another layer to run this script on top of the base container that you're running from. So I'm not going to go into more details about where that container comes from and things like this. Very interesting question, like related to the supply chain of this whole system. But let's just go ahead and run and see if we get the desired result. Which again, what we should expect is just kind of like some printout statement. Okay, so I see the job failed. Looks like maybe I'm in the wrong directory. Yes, so I was looking for this hello world.py file. I see what directory I'm in. I'm still in the root, not this TorchX local. So I'm going to cd into the TorchX local directory. And now let's rerun the same command. Okay, now we see a different result. Now this is the result that we wanted. Essentially what happened is, based on the original image, this is the part that I was explaining about, like kind of adding a layer on top of this default image that TorchX decided to pull. So they've built and pushed a PyTorch image into a container registry. In this case, it looks like it's on Google Cloud. And then on top of that, we're going to run this script with the command that we passed with torchx command. So we see hello PyData. And then if we want to maybe change this, we can change it back to hello PyData Global 2023. And we can kind of get this interactive workflow going. And you might be wondering, like, why does any of this matter, right? I could just run the Python scripts like normal, just do like hello world.py, PyData, and then just like something random. And like you could just run this Python script regular. So why would you want to do this? We're actually like moving in the direction of packaging this up so that we can run it on many different nodes, and all those nodes are going to have consistent compute environments, and we're going to be able to schedule that job as a group. So again, that's kind of like the main thing that I want to point out in this session is like we're just trying to move one step at a time in that direction and like get used to like the core mechanics of what's going on here before we kind of just hit run on this massive compute job that's happening in the cloud. Okay, cool. So that's step one. Now we haven't touched the Minikube yet. So we set up all the Minikube cluster, and then we just ran inside of Docker, which is not interacting with the Minikube yet. Now the next step of what we want to do is we want to run the same exact script that we just ran, but inside of that Kubernetes cluster. And the reason for this is that this is the kind of connection to these massive scale compute clusters, like the Kubernetes cluster that like X is running to train Grok, or that OpenAI is running to train GPT-3. These massive scale compute clusters are existing in the cloud most likely, or in somebody's data center on and we want to kind of have the muscle memory of this section is basically trying to give you the muscle memory of like what does it actually feel like to interact with a cluster like that on a small scale, but with the same exact APIs and code that you'd be using on the large scale. So in order to do this, we need to start using the Volcano system. So the reason that we installed this, again, is it's going to install a bunch of like kind of custom objects into your Kubernetes cluster, is what Volcano is doing. And one of the main ones is going to be the queuing system. So like we'll get into this a bit later, but like Kubernetes doesn't exactly have like batch job support baked into the kind of the base Kubernetes implementation. And that's one of the big things that Volcano is adding to it, is this ability to submit batch jobs and the ability to submit them into a queue. So in order to get a queue set up, we're going to apply this YAML file called queue.yaml. And if you don't know much about Kubernetes, you don't know what YAML file is, don't worry. Like it's not that crazy. Like it can be confusing, but there's nothing that special happening here. Basically, what we're saying in this really simple YAML file is that we have this kind of special API version that comes from Volcano, and like we need to have run that installation command to use this, and that enables us to use this queue object that Volcano provides, and then all we're doing is just naming the queue. You can see that there's a parameter here called wait, that you can think about that as like that's a way to kind of like judge the priority of different jobs. So say you had several queues, or you had several different types of jobs that you wanted to submit into this queue, you can kind of apply different weights to them. Is like that's the core thing that Volcano is providing. It's kind of this in conjunction with the batch jobs. Okay, so we've got this PyData torchx demo queue. Let's go back and actually just run this just to make sure that I have it. Okay, so I see it's unchanged. So I've already run or applied this YAML file to my Kubernetes cluster. And so we can see that it says it's unchanged. Basically, like the queue already exists, and the file that I just tried to change it to doesn't change anything, so do nothing. Now we're going to run the same exact thing. The only command that's changing is instead of the local Docker, we're going to run with Kubernetes. So let's go ahead and submit this. And then we'll say Kubernetes. We'll get a similar build. One thing that's different here in this output is you'll notice that we're actually pushing something to Docker. So in order to use Kubernetes with torchx, we actually had to create a Docker registry. And a Docker registry is basically a place where images get stored. So this is because the containers aren't going to only be existing on my local computer anymore. The idea is that we're trying to like move into this Kubernetes land where the containers are just getting moved around between the container registry and the computers where we actually want to run this PyTorch code. And TorchX is out helping us orchestrate that. But in order to do it, we need a place, like kind of a central place where I can go actually find the images. So in this case, it's in my personal Docker hub. But this could also be a registry. You could also have a registry. Oh, this is going slow. Just get out of it. You could also have a registry on Amazon in ECR, or Google has their own registry, Azure has their own registry, XYZ, for more like kind of enterprise security. Like you should consider doing that. And also, it's going to be much, much faster. Say if your Kubernetes cluster is on Amazon, it's going to be much, much faster if you're storing the compute images that you need to move onto the computers. It's going to be much faster if they're in the Amazon cloud already. Cool. So coming back to what we were doing here, what we can see is that it launched the app and it kind of printed the pod ID of the Kubernetes pod. So connecting back to what we were talking about earlier with the Minikube, they have this wonderful dashboard, and now we'll see that the same Kubernetes pod ID is now appearing here. See that the job was completed. You can kind of click into it and see a whole bunch of useful stuff. But what I want to do right now is just to kind of demonstrate like what the interaction loop is like with the Kubernetes cluster. This is kind of a very vanilla or like day zero sort of interaction with Kubernetes. We can use the Kubernetes command line tool to fetch the logs of that container. So just like when we ran in the local Docker container, there's going to be logs that are kind of printed out to the standard out. So it'll look just like kind of if we had run this in the Docker container. But again, like we're running inside of an isolated Kubernetes cluster on my computer that could be running anywhere in the cloud or anywhere in the data center. And then we can just access those logs seamlessly and kind of get the full observability back there. Cool. So I'm going to pop back to the chat now. That's kind of the end of that section. And then there's going to be a more involved computing section at the close. It looks like good on. Okay, yeah, looks like there's nothing new in the chat. Cool. So I'm going to pop back to the slides for a little bit, just to kind of extend the story in a bit of a different direction and kind of move us back into the Python ecosystem a little bit more directly. And then we're going to run a more serious scale job in the cloud to close out the session. Cool. So now, again, like you can see kind of this little purple dude here, like is kind of symbolizing the like what we just did, like we're that person that's kind of like typing away on our keyboard, and everything I was doing was contained to my laptop. Now it's like obviously I need to get powerful computers. I need to be able to run these jobs in an actual workflow system to like create real software, not just something where I have to be sitting there typing at my computer to make it happen, but something where maybe new data comes into the system, the job just runs automatically, or every week we just kind of rerun the job just to keep things fresh, things like this. So I want to like kind of zoom out and kind of compare AI systems in general and machine learning systems in general to how traditional software works. So historically, we kind of have this valuable system where like the goal of the engineer is to kind of build something that's going to run reliably without a human in the loop. It's like you don't want to kind of have to always be responding to like a request in your product or your application with an engineer actually getting like needing to be in that loop. You kind of want the system itself to be able to make the decision is kind of one of the ways that you can think about building valuable software in general. Now, with ML, there's a whole bunch of new stuff that gets introduced into the system. So the value producing system still needs to be correct and it still needs to run reliably without human supervision. But there's all this extra complexity where now we have this like this purple person, like it's us playing around with the PyTorch code and like building new models. But even more than this, it's like the whole system is starting from data in the real world that's changing. So unlike a kind of rule-based software that says if this, then do that, where producing correct results is much more well-defined. Now we have kind of these like slippery real-world data distributions, and then those are getting pushed through machine learning models that are also based on probability and statistics, and things that can often be kind of hard to control the correctness of, especially recently in this whole like language modeling space. So all this stuff is new and it introduces extra complexity into the system. Um, and I guess to kind of connect to this graphic, the idea is to try and simplify a lot of that complexity and to really zoom in on before we kind of mostly had like the code is what we were focusing on in the traditional software description. And now we sort of have this triad of interaction between data, models, and then the code. So the data and the models, like this is a lot of what we've been talking about so far is like how do you fit the models and how do you fit the data onto the right computers to actually get the models to learn something so that they're useful in your product or application in a new way. The connection here is really compute because in order to make the models learn from data, you need a lot of compute power and a lot of memory on those computers to make it happen. Then to like connect this into a system where you can actually run it on a schedule or you can run it based on new events happening in a system, or even maybe you just need to run a couple different versions of the model in parallel with different hyperparameters, say. You need a system to orchestrate this. So we need a way to kind of connect the different models that get built into the code base that actually defines how those models get trained. And the key thing that like we really focus on at Outer Bounds, and is one of the reasons why I like working at the company, is we focus very much on like what is the experience of the humans, like whether it's this purple person, this like data scientist type, or the yellow engineer. It's built by humans and it's built for humans at the end of the day. So focusing on like what the experience is like to access compute and to build systems that can orchestrate these workflows, it's really important to kind of consider like what is the experience like for these people and how do we make it easier for them to focus on the right layer of abstraction that helps them get their job done, helps them make value for their business, and so on and so forth. The systems are also built iteratively. So it's kind of like another thing to really think about is like how do we kind of orchestrate this whole thing? But then at the same time, like each of those runs of the orchestrated system somehow needs to kind of be versioned because these scientist types, especially the new people that are in the picture producing these valuable software systems, their main job is to be iterating, is to be considering what experiments can we run? How can we consider like putting two models in production and seeing which one's doing better in a more systematic way? Things like this. In that world, versioning becomes extremely important, where we need to be tracking all of our experiments, we need to be tracking all of our results, and then we need to be able to access back to the workflows that produced the models and connected them to the data sources, even the environments that ran on the computers, like we were just seeing with Docker and Kubernetes. Kind of need to be able to version that entire system end to end in order to have a reliable, robust, valuable system. So now connecting this back to like the HPC part of this talk, like there's a whole bunch of stuff in the machine learning stack that has nothing to do with HPC is kind of the point of this slide. The team at Outer Bounds, we work on this open source framework called Metaflow that kind of acts as like a substrate across all these different layers of the machine learning stack. And the compute layer is a very important one, and it's becoming increasingly important for building your own AI systems if you want to say train a large language model or train a diffusion model like Stable Diffusion. But it's still just one component and it needs to depend on enterprise data systems, whether that's Databricks, Snowflake, or an S3 storage solution. And it needs to connect to all these other different layers of the stack to really drive value beyond kind of being an experimental research tool. So I want to show you quickly how Metaflow actually does this. So this link is going to go back to the same repository, but just to a different part of it. And that's going to be in the torch run cluster. So what exists here is essentially very basic instructions. It's really high level. So if you need help, please reach out on Slack because like I'm not expecting people to be able to follow along right now. It requires that you have a full deployment of Metaflow, which I can show you. The documentation is here. So go ahead and link this. And then if you're looking to get started with Metaflow, we have a bunch of instructions on how you can do this, like how the engineering resources work, which this is the kind of the ways that you can deploy it on your cloud. You can also deploy it on premise. But the main idea here is that Metaflow is kind of acting as a layer that connects your Python code, your PyTorch scripts, very similar to how we were seeing with TorchX. And it does this in a very general way that's not unique to PyTorch, scikit-learn, any kind of system that you might want to build, or any data engineering framework. But it kind of connects your Python codes in your Jupyter notebook like layer of thinking into these like production systems. So you can have one of these like yellow hat people, one of these platform engineers say deploy Metaflow once, and then you can have many scientist types all be kind of submitting their jobs to it, running them on a schedule, running them when new data comes into the system, these kinds of things. So what we want to do is run, let me actually just go to VS Code, it'll be easier to see everything. What we want to do is go into this torch run cluster directory. So I'll go ahead and do this. And we're going to run a GPT model. So we're going to train this GPT model. And this is coming exactly from Andrej Karpathy's MinGPT repo. If you're not familiar with that, it's definitely worth checking out. I think it's about a year old now, but he wrote this excellent repository that is one of the simplest implementations, maybe the simplest implementation of what the GPT models are, like what these transformer models are. So this repository has a bunch of like excellent PyTorch code that's really easy to read. I mean, you can see as evidenced by 2,000 people have forked this repository. It's really kind of like made the waves in the machine learning community. But basically what we're going to see here is how you can run that training code in a few lines of Metaflow code. Well, I should say the PyTorch code is the exact same, but we're kind of connecting it into Metaflow as a workflow system. So we're kind of building on top of his research code and then just plugging it into a machine learning orchestration system that's going to help us run it and get access to all those resources without having to think of it. Kind of like calling back to the idea of like, we want to separate the concern of like, how do I get access to the compute, to the research cluster? And then like how do I like actually write the research code? And we want to kind of like separate those two things, which is what we're demonstrating here. So in order to run it, there's a very simple command that you can do with Metaflow. I'll actually just type it out, python.py. Its package suffixes is we just are telling Metaflow that we want to include a YAML file in the run. Actually, I'm going to need to go into the MinGPT repository. You see here. And then I'll copy paste this command and run it. And I'm going to explain what's going on here because this is going to take a while. Because what we're actually doing in this case is we're going to be submitting a job to run on AWS Batch. And that's going to have 8 GPUs on each node. And we're going to run 2 different nodes of that job. So this is kind of getting even further in the direction. So like before we ran on a local computer, now we're running in the cloud on multiple nodes in the cloud. And you can imagine kind of like scaling this out. And then like one of the main value propositions of Metaflow is that if you say want to switch from AWS Batch to Kubernetes, it's very, very easy. I'll just show you in 1 second here. Before I talk too much about like kind of how Metaflow is communicating with AWS Batch, I just want to like connect fully to the research code. So you'll see here we have this torch run argument, which this is very, very much like the command that we ran in the terminal before to use torch_x to run a Python script and then say pass some parameters into it, things like this. So what we're doing in this current.torch run command is we're passing an entry point file, this main.py file. And this just contains the pre-existing research code from Karpathy's repo, essentially. So the idea is that like I didn't need to modify any of the research code. I was just able to plug it directly into a workflow orchestration system that has the ability to access like huge, powerful computers in the cloud and kind of on demand build me a small but like very powerful HPC cluster. And you could totally scale this up. Or you could use it with on-premise resources in a static compute cluster. Like again, if you kind of own your own GPUs and want to connect such a system to that. So what this research code is doing is this main function is just kind of setting up the distributed data parallel. So we kind of talked about the difference between data parallel and model parallel earlier. In this case, we're actually seeing an implementation of data parallel in PyTorch code. We're loading up a bunch of different config files, one for the model itself, one for the optimizer, one for how we're going to load data onto each computer. So remember in the data parallel case, like each computer is going to get a different slice of the data. And PyTorch has a bunch of really nice features built into it to make that a super easy operation for you. And then the core thing that we're doing here is just calling this trainer.train, which that's actually what's going to kick off the process where the model learns. So if you're curious, you can go more into this trainer file. This is where the actual magic of that is happening. So you can see like the important part is going to be this train function. This is kind of the core loop that's like running the different epochs of the neural net training. But that's not really the main focus of this talk. So I'm going to go back to the workflow file. Again, this is the thing that calls that main script. And the reason to kind of like separate the research code from this workflow file is now the workflow itself becomes this like nice little package of, what is this, 48 lines of code, where we can call that script, and then we can have it run in a bunch of different ways. So right here, what we're saying is like, okay, we need to pass some environment variables in. I know that we're going to be running on GPUs, so I want to actually profile the utilization of my GPUs. All these little decorators, these little @ symbol like annotations on top of the function. These are kind of like Metaflow syntax for adding different features that are inside of Metaflow to run this code. But like in this case, we have the GPU profile, which this is saying like I want to track how much memory, how much of the compute basically am I using on the machine. So after I run this once, maybe I'll have, okay, I only use 60% of the resources. Maybe I don't need such a big GPU, something like this. Or even more, you might see where your code is bottlenecked and kind of see how to change things. But then the two big decorators that we're using here are this @batch and @torch_run. So the @torch_run is what's enabling us to kind of get this extra ability to specifically submit a torch script and run it like we saw with TorchX earlier. And then the @batch is what's connecting us to AWS Batch. So when you deploy Metaflow, there's a bunch of templates where you can essentially kind of print the whole Metaflow stack inside of AWS, Google Cloud, Microsoft Azure. And in this case, we're using AWS Batch as the compute backend. So AWS Batch is kind of a solution that's built on AWS for exactly this kind of thing. And they have this notion of a multi-node job where you can have many different computers kind of spin up, run a container, just like we saw with the Kubernetes on the Minikube cluster, and then have those containers communicate with each other for something like distributed data parallel or for model parallelism, whatever. There's not too much else here. So maybe what I'll do is actually just log into the AWS console and I can show you what's going on in a little bit more detail. Okay, so here's kind of like the base view of the AWS console. If I click into the batch part, you can see a bunch of different job queues. So earlier when we were going through the Volcano example on the Minikube cluster, remember we manually created a queue and we needed to install Volcano to do that because that doesn't exist by default in Kubernetes. That does exist by default in AWS Batch. And it's part of the benefit maybe of using a managed service is that feature just exists already for you in AWS Batch. So if we go back to kind of referring back to this picture, right now we're kind of in this middle bucket. Whereas before, when we were doing the Minikube business, that was more in this top bucket. So like maybe one benefit here is like the queue is already created for us essentially as a feature. And I can just go to job queues and kind of click buttons and make the queues happen this way. Now, of course, in practice, you might not want to do that. You might want to do it all programmatically, which is something that the Outer Bounds team can definitely help you out with. But essentially, you can see that we have all these different queues, and the job that I've submitted is running in this queue. So we can see we have a multi-node job. Again, remember we had 2 nodes. So Metaflow is helping us specify in our Python code that I want 2 nodes to run on AWS Batch. And I want each of them to have 8 GPUs. We can see that the job has the status of starting right now. So whether you run on Kubernetes, AWS Batch, it's very important to have some system for monitoring the life cycle of these jobs, especially ones where we're requesting pretty massive amount of resources here on each node. So it makes sense that it's taking a little while for AWS to provision those resources for us. So like that's basically what we're seeing here is we're seeing Metaflow kind of propagate these logs of statuses starting. We can click into the node and kind of see a bunch of different information on AWS Batch about what's happening here. Like in particular, you can see like a bunch of confusing stuff here, which is okay. I don't want to say it would be this bad, but like the experience of maybe using something like AWS Batch without a system like Metaflow or TorchX is that you kind of have to like get into the level of like actually submitting commands inside of a like figuring out what command to run inside of the container that AWS Batch sees. Whereas with Metaflow, remember all we did was we just ran this command in the terminal. So basically like regular Python script command plus a couple arguments and then run. And then Metaflow kind of took care of packaging up all that stuff for us. And it sort of took care of like specifying all the different resources we needed in the batch containers, as well as preparing things like environment variables and doing a bunch of other fancy stuff on top of it. So what we're seeing now is that Metaflow is now kind of taking all of the different things that are happening in the rest of the cloud system. So it's like kind of setting up an environment, meaning that in this case, this could be like a Conda environment or a set of packages from pip. But in this case, what we're doing is we actually built a custom Docker image. So similar to the Minikube case that we saw earlier, there's like somewhere existing, there's this Docker registry that I've created. And then there's a Docker image called MinGPT that's tagged with the label 3. So we're kind of telling Metaflow here, like pull that into the AWS batch container that we want to run here. So that's what it's doing when it says setting up task environment here. And then it's going to go ahead and run the code in this job, which again is just running this training loop here. So we should see that start to happen in a few minutes. Maybe it can take like in between 5 and 10 minutes to run jobs where we're requesting kind of these big computers. So yeah, that's kind of like the super high level. I'll go ahead and check if there's any questions. Oh, looks good. Let's see. Another thing that I can show you while we're waiting here is that Metaflow also has a UI. So like before we were kind of monitoring on this Minikube user interface, Metaflow also has a user interface for monitoring jobs that we submit. So you can see here, like myself and a bunch of teammates have been submitting jobs to this same deployment of Metaflow. And earlier I was saying that the workflows being versioned becomes extremely important, like whether you're doing HPC work or whether you're doing kind of just like regular data processing or more data engineering pipelines, whatever kind of AI, ML system, data system that you're trying to build, you kind of want to version these workflows. So we named this one MinGPT, which is matching the name of the class that we created here for our workflow definition. And if we click into it, we can start to see what's happening. So you can see that there's 2 nodes running. Again, we're in 2 in parallel, kind of starting up. We can see the task logs getting going. So we should expect to see the training loop starting soon. But Metaflow has a bunch of different functionality built into this UI to help you monitor jobs, kind of like help you do data visualization, outputs, sort of build these dashboards that you can then send to some end user or maybe like a business executive that wants kind of observability into all the different workflows running in a production system, or a development system where like something like HPC might be more common. See if there's any more slides to go through. Well, that's going. I kind of just want to zoom back out, maybe do a quick summary for a couple minutes, and then save time for any questions at the end. If we have a couple more minutes. Essentially, what we've talked about today is that the cloud is here, and everyone's kind of moving to the cloud. This is inclusive of these like very demanding, compute-intensive AI workflows. Recent events have made it even more kind of in demand to do things with AI. And we talked about sort of the different ways that the leaders in the AI community are demonstrating that there's a couple different parameters that you want to be able to scale up. And we kind of made the arguments earlier in the presentation that compute is one of those ones that you can invest in. that investing in it in the cloud is becoming an increasingly good option. And then to do so, we need some systems for running these batch jobs, whether it's AWS batch, like we just saw, whether it's on Kubernetes, um, with like kind of these custom operators like Volcano, which is a very active kind of realm of R&D if you're a Kubernetes expert. Whatever the case may be on how you actually get the infrastructure available to scientists, the compute primitives are very similar to kind of traditional HPC workloads. So there's a lot of things that we can learn from systems like MPI. We might even want to be using MPI. Then we kind of like saw how that connected to Torch Run and how like the most common way to run these PyTorch models right now is typically using the Torch Run or using MPI. And then finally, like we kind of saw how Metaflow can help you take these HPC primitives and make them more accessible to data scientists, make the clusters easier to manage for engineers, and kind of help you just get going fast and then figure out where the optimization targets are if optimizing the HPC cluster is really within scope at your organization. Let's go ahead and see if we've got any results coming in. Okay, awesome. So now we see our job is actually starting to run. So we're logging kind of the loss curve of the neural network training. So we have a bunch of different GPUs all contributing to the same job. They're kind of spitting out the logs here. And then if we go to the other task that's running, because remember we have two nodes, we'll see that they're all kind of aware of what's happening in the rest of the ecosystem. So they're starting the GPU index in this case from 8 through 15, because the first one's going from 0 to 7. So we kind of see that all 16 GPUs are contributing their resources to the same neural network training here, which that's essentially the punchline of the demo. Not too much interesting in these logs beyond kind of seeing that. So I'll pop back over here and then just wrap up quickly. Yes, if you're interested in this stuff, and Metaflow sounded like an interesting tool for you to check out. We've been writing a bunch of blog posts about this lately. Here's two of them. The one on the left is kind of an introduction to how we view the compute layer in that machine learning stack diagram. And then the one on the right is showing you like what we just saw is how to use this @torch_run decorator. But we've made some other ones as well, and are working with the Metaflow community on building more. So you can check out those two posts if you're interested. There's a bunch of stuff to learn about doing HPC in the cloud. I really like the Slurm, the introduction YouTube series. I think is really good. It's a really good framework, even if you have no intention of using Slurm to learn from. There's a bunch of great resources coming out these days around Kubernetes eating high performance computing. It's kind of a very desirable thing for a lot of folks, and there's a lot of great Kubernetes engineers out there. So that's a really good set of resources to learn from. Also, all the cloud providers kind of have their own incentives, I guess, and their own kind of product lines built around doing distributed training in different ways. So like there's kind of these like HPC fundamentals style information, like the HPC tech shorts from AWS or the cloud HPC toolkit from Google. There's also just like the basic Kubernetes cluster resources that are very helpful if you want to use Kubernetes to do this kind of stuff. And then that kind of third bucket, the highest level, maybe the fastest way to get started, kind of these SageMaker like APIs. It's very useful too if you're kind of trying to fast track how your organization can get going to take a look at those. And to close out, definitely check out Metaflow. Check out Outer Bounds if you're interested in kind of a managed version of Metaflow, or if you just kind of want to get in touch with the team that's doing a lot of the building of Metaflow and the maintenance of it. We also have two more talks. So Outer Bounds CEO Ville Toulos is going to be giving a talk called Compute Anything with Metaflow. So sort of a little bit higher level than this talk, but he's going to be talking sort of about all the different ways that you can use Metaflow, like far beyond HPC. That's just kind of a tiny slice of the world that he'll be presenting. And then our head of developer relations, Hugo Bonne Anderson, he is giving both a talk and a tutorial. His tutorial is at 1 Pacific time today, where he's going to be going through some of the fundamentals of using Metaflow. So maybe like a lot of the stuff that's kind of prior to this more involved high performance computing way of looking at Metaflow. He'll be kind of looking at the more basic fundamentals, like how does this just help you build robust software systems in general. So definitely check out those talks. I'm sure they'll both be really interesting. And then finally, we have a very active Slack community. So if you want to join, over 3,000 now data scientists, software engineers, people thinking about all the stuff that we were talking about today, join our Slack, and feel free to reach out. I'd be happy to connect with any of you. Thank you. Please, if you have any questions, I'll monitor the chat now. Does Metaflow work with Keras? Yes, absolutely. Metaflow works with Keras. So there is a bunch of resources here at outerbounds.com that I can point you to in the how-to guides. I believe there's one for Keras. Yes, so right here, I can paste the solution. This is like a kind of a higher level. Like there's a lot of different ways that you could integrate Metaflow with Keras. But I guess the real punchline is that these workflows that you write with Metaflow, they're all following the same structure of subclassing this flow spec object. And then the functions of that object are the steps in your workflow. You can put any Python code in here, is really my point. So this is inclusive of any Keras code, any NumPy code, PyTorch, XYZ, scikit-learn. Yeah.